Today, we're diving into a technology that sounds like something straight out of science fiction. It's giving scientists a kind of superpower, the ability to see the actual chemistry of a disease happening inside our cells. It's called MALDI Imaging Mass Spectrometry, or just MALDI IMS for short, and honestly, it's changing everything. So let's get into it.
You know, for hundreds of years, medicine has depended on the microscope, right? You stain a tissue sample, you look at the cell shapes, and you make a diagnosis. But here's the thing, that only tells you part of the story. It shows you the structure of the problem, but not really the why. I mean, what if you could actually see the chemical signals, the tiny conversations happening between those cells? What if you could pinpoint the exact molecules that are making things go wrong? And this right here shows you exactly what I'm talking about. On the left, you've got your standard microscope view of cancer. You see the cells, the structure, it's what we're used to. But on the right, wow, that's the same exact tissue but seen through MALDI MS. All of a sudden, this vibrant, colorful map of molecular activity just explodes into view. It was there all along, completely invisible to us. That's the hidden world this technology opens up.
Okay, so what is this thing? This molecular map maker? Well, MALDI IMS is basically a technique that creates these incredibly detailed 2D maps. It shows you exactly where hundreds of molecules are located on a super thin slice of tissue. The best way to think about it is like this. It's what you'd get if you smashed a high-powered microscope and a mass spectrometer together. You get the what and the where all at once.
And the power here it's just incredible. In a single experiment, you can map hundreds of different molecules at the same time. But here's the real kicker, the part that makes it so revolutionary. You don't need any special tags or labels. Normally in biology, you need an antibody or a stain to find what you're looking for. Not here. You don't even have to know what you're looking for. You just look. It's a pure discovery tool tying the chemistry of a sample directly to its physical structure. All right, so how does this magic actually happen? How do you get from a piece of tissue to one of these incredible molecular images? Let's break it down and follow a sample step by step on its journey.
It really all comes down to 4 main steps. First, you get the sample ready. Then, you apply something called a matrix. After that, a laser does its thing. And finally, you visualize all that amazing data.
Okay, step 1. It all begins with the sample. You take a piece of tissue, flash freeze it, and then slice it unbelievably thin with a machine called a cryomicrotome. And you can't overstate how important this step is. Seriously, scientists in the field will tell you that sample prep accounts for like 99% of your success. If you mess this up, the whole experiment is a wash. The key is to lock every single molecule in place exactly where it was in the living tissue. All right, next comes the M in MALDI, and that stands for matrix. This is really clever. You coat the tissue slice with a super thin, even layer of a special chemical. Think of it like a primer you'd use before painting. Its whole job is to absorb the energy from a laser and then gently help lift the molecules off the tissue so they can be analyzed. It's the key to getting them into the air without just blowing them to bits.
So now we get to the cool part, the laser. A laser beam scans across the entire tissue sample, zapping thousands and thousands of tiny spots. At every single one of those spots, and each spot is basically a pixel in our final image, the matrix does its job. It absorbs the laser energy, and that energy gently lifts molecules off the tissue and gives them an electric charge. Then, a detector measures the mass of every single molecule that comes off that one specific spot.
And that brings us to the big reveal, the visualization. This is where all that raw data becomes something beautiful. The software takes the information from those thousands of laser spots and stitches it all together into one coherent picture. You can then basically just tell the computer, hey, show me where all the phospholipid and choline is. And boom, it generates a heat map showing you exactly where that molecule is and how much of it there is. You've essentially created a chemical layer on top of the physical anatomy. It's amazing.
Okay, so this is all really cool technology, right? We can make these gorgeous molecular maps, but so what? What do we actually do with them? Well, this is where it stops being just a cool technique and starts being a total game changer for medicine.
One of the absolute biggest uses is in discovering biomarkers. Take breast cancer, for example. Researchers have found that normal tissue and cancerous tissue have totally different molecular fingerprints, especially when it comes to fats, or lipids. You can see it right here. The healthy tissue is loaded with one kind of lipid, while the tumor area is just glowing with a completely different kind. Being able to see these patterns, these chemical signatures, could be a massive leap forward for getting more accurate diagnoses and getting them earlier.
And check this out. This concept is so powerful. It's called virtual microdissection. Normally, if you wanted to analyze just the tumor cells, you'd have to physically cut them out with a tiny laser or a needle. It's really hard. But with this, you just do it on the computer. You draw a circle around the region you care about, maybe just the tumor cells or the healthy cells right next to them, and the software instantly tells you the unique chemical profile of only that area. It's literally like having a molecular scalpel, but with a mouse click.
And it doesn't stop there. The possibilities are just huge. Scientists are using this to tell the difference between tumor types that look identical under a microscope. They're using it to track a drug inside an organ to see exactly where it goes and what it turns into. They're finding markers that can predict if a chemotherapy will work for a patient. They're even using it to tell the difference between diseases like Crohn's and ulcerative colitis, which can be really tough to distinguish.
I mean, the potential is so massive that a couple of the pioneers in this field, Norris and Caprioli, basically said that MALDI imaging is on track to completely revolutionize the entire practice of pathology. They believe it's going to provide the next generation of diagnostic tests that will improve and extend people's lives. That's a huge statement.
Now look, the technology isn't perfect. Not yet. But the future for it is incredibly exciting. So let's talk for a minute about the current hurdles and what's coming next.
So there are a few big challenges. That sample prep we talked about, it's still a bit of an art, and the goal is to standardize it so results are more reproducible everywhere. The matrix chemical can sometimes cause its own problems, so people are even working on matrix-free techniques. And of course, there's the big one, the push for more detail, higher resolution, and faster scans. The dream, really, is to get these chemical maps down to the level of a single cell, or maybe even see the chemistry inside the different parts of a cell, and to do it all in minutes, not hours.
So what we're left with is this incredible new window into biology, a tool that lets us map the chemistry of life right where it happens. It's already changing how we think about everything from cancer to how drugs work. And it really makes you stop and think, doesn't it? Now that we can see this layer of reality that was always invisible, what other hidden worlds are we going to find next?